This is Carol Sweeney from the Department of Internal Medicine, University of Utah. This is a lecture segment on measures of disease frequency, concepts of survival analysis. Now there's a preceding segment that is measures of disease frequency with concepts of incidence, and if you haven't, this really leads out from that. So if you haven't viewed that one yet, I would encourage you to go back and view that one first. The objectives for this lecture segment is that students will understand the data structure that underlies survival analysis, and that students will be able to interpret a Kaplan-Meier plot. So survival analysis is actually considered a fairly advanced statistical area. It can get very fancy with the math. It can just get very, very elaborate. So normally an introductory course does not say much about it. But in the medical and clinical literature, you are going to see this applied in the articles that you read over and over again. You see so much survival analysis, you see so many Kaplan-Meier plots. So in this lecture, I'm going to just try and introduce you to these concepts, not getting into the math or the weeds at all. And if you're interested in that, you can pursue some true statistics courses. Okay, so the outline of the lecture will be that we'll talk about the proportion surviving in a closed population, the proportion surviving in a dynamic population, and survival data structure and the Kaplan-Meier plot. So the concept of survival, often in clinical studies, there's an interest in estimating survival, that is to say, the proportion of the population who are alive or free from an adverse event over time. This concept, though, is very closely related to incidence, which we talked about in a prior lecture segment. So in fact, we can take some of the same graphics that I like to use for incidence and instead think about survival analysis. So now say that this is your study population with whatever chronic disease, and you're interested in what influences mortality in this population. So we're going to start when they're all alive. They all have been defined as having the disease, and they're at risk of mortality from this chronic disease. So as time goes along, we're following them, and mortality events are happening. Okay, same graphic, same concept, at least to me. And again, we can create a graphic like this, thinking about each person and their survival experience from left to right. Now I can take the same graphic and change it slightly. Now I've gotten rid of the blue circles representing each event, and instead what I've done is I've taken the horizontal line and stopped it when that event happens, and then I've drawn a little vertical line connecting down to the next level when that survival event happens. And over here we had 2 mortality events, and so our curve has dropped by 2 units. Over here we had 1 and it's dropped by 1, so on and so on. So if we actually got rid of all the horizontal lines underneath and we just left this shape at the top based on the curve dropping each time there is a mortality event, that right there is our Kaplan-Meier plot. It's really that simple. But it's that simple in the assumption that you have a closed population and that everyone who has not had a mortality event is followed through to the end to time t. So where it gets a little fancier is when you have a dynamic population. But returning to the closed population, in the closed cohort, over any time interval, the proportion surviving equals the number of individuals still at risk at the end of the interval divided by the number at risk at the beginning of the interval. It is also 1 minus the incidence proportion. So if we divide the follow-up time into smaller intervals, note that the product of the proportion surviving over each interval equals the proportion surviving calculated over the whole interval. So I'm actually going to show you this calculation. It's really pretty simple arithmetic, but let's go ahead and go through it. So here's our same group, and I've just arbitrarily marked time units 1, 2, and 3 here. So the portion surviving over the whole interval from 0 to 3, 17 people are left in the population by time 3. We started with 25, so 17 over 25 is 0.68. That's the proportion surviving at time 3. But if we go ahead and divide this into 3 different time intervals, we can calculate the proportion surviving across each interval. So from 0 to 1, we started with 25, that's the denominator. We lose 4, so our numerator becomes 21. 0.84 is our proportion surviving. And then between time 1 and time 2, we start with 21, that's our denominator. The number surviving is at the end is 19. 19 over 21 is 0.9. and then from 2 to 3, the same thing. So you'll note that the denominator is changing each time the number entering the interval gets lower. But the further interesting thing here is that if we take these three proportions, 0.84, 0.90, 0.89, multiply those together, we happen to get 0.68, which is exactly what we got when we calculated over the whole time interval. So this is useful if you're interested in a particular time, if you think that events are not constant over time, but where it's really useful is when we get to the idea of our dynamic population. This idea of breaking the survival into time intervals is going to help us solve the problem with a dynamic population. So here's our dynamic population. Again, we have people who had a mortality event with blue circles and people who were followed for a period of time, did not have a mortality event, but then their follow-up has ended, which is represented by the open circle or censoring. So when subjects are censored, an unbiased estimate of proportion surviving can still be made. The approach is to divide the time into intervals and include the censored individuals in the calculation for the intervals during which they were observed. So that is the key there, is that people who are, again, if they were only enrolled in your study one time unit ago, you only have one time unit of follow-up, you don't exclude them from your data analysis, you include them for that one time unit where they were followed. And actually that is the way to avoid bias. Excluding people with shorter follow-up actually introduces bias in your study. So in this case with a dynamic population, I have calculated the proportion surviving from time 0 to time 1. 24 study participants entered at time 0 and 20 were left free of an event at time 1, so we get 0.83. And then I've got several different time intervals from 1 to 2. We have 17 completing it and 18 who started, time 2 to 3, 16 who started and 15 who completed, and so on. So the denominator is changing not only based on the number who had a disease event, the denominator is also changing based on who was censored and is no longer under observation. So if I calculate all these intervals for this graphic that I've drawn, and then I multiply all those proportions together, the time interval specific proportions, multiply them all together, and I get over here 0.63. And that is my unbiased estimate of the proportions surviving over this time interval. So the survival data structure, so if we took that graphic that we just looked at and we wanted to put it into a computer and get the computer to calculate proportion surviving for us and generate a Kaplan-Meier curve, we would need two values for each observation. We would need time and failure. Time is the time after which they are no longer under observation. So time is going to be a continuous variable, but it's restricted to positive variables, right? So 0 to positive infinity is what the time variable would look like. Failure is the general term for the outcome of interest. So failure is sort of the statistical term. So if your outcome of interest for clinical reasons is incident disease or death or recovery or relapse, whatever it is, statistically we're going to call that failure. So usually coded 1 for fail and 0 for censored, or 0 for not having the outcome. So here's the data set that I generated to match that graphic that we were looking at earlier. So each subject is going to have a study ID, and I've just numbered them 1 to 24. And then T is going to be our time variable. So these first 4 people all have 1 unit of time that they were observed for the study, and all 4 of them had blue circles at the end. They had the event, so they are all 1s for the failure variable. But then down, and we've got some other people with different time under observations who also failed. But then down here, we've got people who have different amounts of time that they were observed, and they have a 0 for fail because they were observed to the end of that interval, whatever that time is, without having our outcome event. So here's our person who was only observed for 1 unit of time. Participant 12 was observed for 1 unit of time and did not have a failure outcome, so that is how we code them. So that's how you want to think about capturing your data when you are doing any kind of follow-up study. And through the magic of statistical software, we can set this up and we can ask what are the survivor characteristics of this population. And it says, well, we had 24 observations, 8 of them failed. 94 is the total analysis time at risk. And then this is our survivor function. So this is telling us that at time 1, the proportion surviving was 0.83 based on 24 entering interval, 4 failing during the interval, and 2 being lost to follow-up at the end of the interval. And so on. At each time point, it is estimating a proportion surviving. So we can literally take the numbers from this from this column, from the survivor function column, and we can plot those to create our Kaplan-Meier function. So you could literally do this with a pencil and paper if you wanted to or needed to, but nowadays it's much more common that people are using statistical software for this. But each of these inflection points represents a proportion surviving that we saw in the previous slide in the output. So what's happening here? So this axis on the left goes from 0 to 1. This is the proportion surviving from 0 to 1. This axis is the analysis time. So at time 0, you have a proportion surviving of 1. Everyone is in the study at time 1. We followed them over time, and some disease events happened, and therefore you see the vertical here when an outcome event happens and the graph drops. And so the new proportion surviving is this value here. And then you follow along again until some outcome events happen, and here's the graph dropping again. So if you have a small enough study population, when you look at the Kaplan-Meier survival curve, you literally see on the curve when each outcome event happened. If you have a really large population and a large number of outcome events, these become so tiny that it starts to look like a smooth curve. So then the interpretation is that at any point along here, say I want to know what is the proportion surviving at time, I'm just going to say 3.5. Okay, so if this is 3, this is about 3.5, and I can look at my curve and I can say, oh, well, at time 3.5, proportion surviving was 0.75, and I can then compare that to, compare that proportion in the treated to the untreated, or whatever my purpose was for drawing this curve. So in summary, when subjects are censored or have different amounts of time under observation, an unbiased estimate of the proportion surviving can still be made. And the situation of subjects being censored is really more the rule than the exception. For survival analysis, each observation has a value for 2 variables, time and failure. So when you're conducting a study, you want to think about collecting the variables in that structure.